Good morning. I'm Spot on Weather meteorologist Matthew Euler, and today we're going to continue our discussion on mid-latitude systems. We're going to move into part 3. So let's start talking a little bit. We left off yesterday on the last video talking about baroclinic lows, self-development of those baroclinic lows, as well as Pedersen's rule. All very important processes. All the pieces from the ground all the way up into the upper atmosphere is essential for all these pieces to align together and work together in the development of any low pressure system at the surface. So I'm going to start today's video with a summary of the process of the development of a baroclinic low. So initial conditions, you have what's known as a baroclinic zone, which is located downstream. In the northern hemisphere, downstream would be to the east of the long wave trough axis. You have either a slow moving front or some type of temperature or thermal gradient. So you're in an area downstream or to the east of the long wave trough axis where we have a temperature gradient. We have a slow moving front, perhaps a stationary front. That's ingredient number 1. A baroclinic zone is that battleground between much colder air to the northwest and much warmer air to the southeast. So a baroclinic zone is a zone that sets up in the atmosphere that acts as that battle front or that battle zone between contrasting air masses. Right, so the first thing that happens in this example, what I'm showing you in the graphic, is we have a stationary front. We have the stationary front with colder temperatures and lower thickness values. The dashed lines are indicating thickness values ranging from 540 to 558 decameters in thickness. And we have a shortwave trough at 500 millibars, that solid black line to the left of the graphic, with an area of positive vorticity advection, the red shading, that little circular area, the oval area. We have positive vorticity advection that is beginning to move closer to that stationary frontal boundary. So this is what gets things going. This is what kicks things off in the development of an area of low pressure or a storm system at the surface. Next step. We get that 500 millibar vorticity, as I just showed you in the graphic. That shortwave trough is approaching that baroclinic zone or that weak frontal boundary, stationary frontal boundary. Once that positive vorticity advection ahead of the shortwave trough interacts with the surface front, you get divergence aloft or the removal of mass aloft over the baroclinic zone, and that will start taking the mass and removing it higher up in the atmosphere. And that will start initiating lower level convergence and rising air motion. The surface and thickness, the baroclinic zone, and the surface front itself separate the colder air from the warmer air. As I mentioned, the baroclinic zone, I'll have to show you an example of that on a satellite image, what it looks like in a future video. But the baroclinic zone is almost like an S-shaped cloud structure that kind of it extends from, usually in the United States, it extends from southwest to northeast. Fronts are usually, again, stationary or slow moving, as I've already mentioned. Once that upper level shortwave trough at 18,000 feet or 500 millibars, that positive vorticity advection, the upper level divergence, interacts with the front, an area of lower pressure is going to form along that front. So we have an area of lower pressure forming along the front. So we're getting development of a baroclinic low or a storm. Sometimes we refer to these areas of low pressures as waves. The atmosphere really simulates more of a wave, a fluid wave type structure. And this graphic is just showing you we have an area of surface low pressure, 1,008 millibar low, central pressure, and to the northwest, basically stacking back, up at 18,000 feet or 500 millibars, there's an X. The X represents a vorticity maximum values of vorticity, and an area positive vorticity advection is out ahead of that shortwave trough in that vorticity maximum, and that's now kicking off the development of a wave of low pressure along the frontal boundary. The shortwave trough, as that nears the surface front, the divergence aloft, again, ahead of that shortwave trough starts to occur. We get a stable low pressure wave that forms along the front. So once that wave develops along the front, indications of wave formation, how can we tell if a wave or an area of low pressure is formed along the front? Well, once that happens, we get winds at either side of the front that are going to turn inward toward the front. A frontal boundary is basically an area of low-level convergence in the atmosphere, where the winds basically come together along the frontal boundary. Often this inward turn is most pronounced on the cold side of the front, and this inward turning often is in response to falling barometric pressure. Again, because a frontal boundary is an area of lower pressure, the pressure is going to fall in the vicinity of it. And you get surface convergence is going to be increased. Now, precipitation in the region due to the rising air motion, the cooling, the saturation, eventually condensation and formation of clouds, precipitation in the region starts to increase, and satellite imagery will show a more widening of the cloud band. As that low pressure or storm or atmospheric wave intensifies, we get self-development process to occur as the frontal wave and upper level shortwave interact with each other. Once you get the interaction, you get thermal advection. Basically, you're getting colder air pouring southward, you get warmer air moving northward, and you're creating a sharper temperature gradient. And that is definitely necessary as part of the energy for the storm to intensify. So you get this thermal or temperature advection, movement of different temperatures, warm air typically to the north, ahead of the cold front, ahead of that low pressure system, colder air on its backside, and that will then cause an amplification in your shortwave trough in the middle levels of the atmosphere. We talked about that with baroclinic instability a couple videos ago. Vorticity maximum, values of maximum vorticity will then move into the base of the trough. They'll strengthen. You get increased cyclonic curvature of the trough and strengthening of what's known as cyclonic shear near the trough axis. So you're having a greater turning of the winds along that trough axis in a cyclonic or counterclockwise manner in the northern hemisphere. So as the wave intensifies, look at the image on the right. Notice if you compare both images, the one on the left to the one on the right, you'll notice the wave amplification above the actual surface low and the surface fronts. That wave is starting to get, the trough is digging deeper, the ridge is building, and you're getting a greater vorticity gradient aloft at 18,000 feet. So we're increasing the positive vorticity values, and then at the same time at the surface, that interaction of the shortwave trough with the low pressure, the divergence is increasing aloft, and that is resulting in the removal of mass much more quickly and efficiently over the top of the area of low pressure at the surface. And that is causing an evacuation effect over the top, and you're getting stronger rising vertical air motion in through the center of the low pressure. As the air rises much more strongly in the vertical, the barometric pressure continues to drop or fall, and that is resulting in the intensification of this wave of low pressure. Now, the thermal advection pattern, the temperature pattern, the changes in the temperature become significantly stronger, as does that vorticity up at 500 millibars or 18,000 feet. The frontal wave eventually will become unstable and will continue to amplify over time, and your surface low is rapidly deepening where that barometric pressure is falling off quite rapidly at this point. Cyclogenesis is aided by a local increase in the thickness values, and it generally occurs ahead of the surface low in the warm sector of the cyclone. A mature wave is the next phase of the baroclinic low. So as self-development continues to occur, the wave or low pressure is going to reach, that storm is going to reach its maximum intensity. And this is when you have typically the heaviest precipitation, the strongest winds. And I can remember the storm in early January 2018 here in Southeast Virginia. We had blizzard conditions. We had winds gusting over 35 miles per hour and fairly moderate snow falling across the area. And that was the point at which that particular wave off the East Coast had become mature. Now, at 500 millibars, that shortwave trough begins to close off up at 18,000 feet. What I mean by close off is it becomes more circular to where we have a closed height contour around the upper level low, or that trough. Vorticity maximum reaches its peak intensity during the mature wave stage, and positive vorticity advection, PVA, is intense at the beginning, but then it starts to weaken rapidly as the vorticity maximum becomes pretty much aligned with that closing low pressure aloft, that lower height aloft, height center at 18,000 feet. And the vorticity and height contours become more parallel to one another, So that means that we're not getting any more of that vorticity advection, and the vorticity overall is decreasing. Here's an example of a mature wave. This is the most intense stage of the baroclinic low. And you notice above, basically the top portion of this graphic, you notice that 540 decameter line, geopotential height line. You notice how it's now become closed off, or that dark solid 540 line is basically encircling the upper level low at 500 millibars completely. And then at the surface, we're at our peak intensity. We have our lowest barometric pressure. Most likely you'll have, if it's a wintertime situation, you'll have the heaviest snow to the northwest of the surface low. That's where it's going to be falling. You'll have your heaviest overrunning precipitation north of the warm front in the warm sector. If you have the right dynamics in place, you can even get what's known as a squall line into the deep south in the wintertime out ahead of the cold fronts with these very tightly wound storms. The surface and thickness, the surface low, basically goes through what's known as an occlusion process. I talked about that, occluded fronts, in one of my previous training videos. So take a look at my frontal systems video for what an occluded front actually is. It's pretty good material to take a look at. Basically, once the surface low is occluded and reach peak intensity just after occlusion is typically when that occurs, the vertical tilt between that 500 millibar low, upper level low, and the surface low pressure will decrease. So now we're not getting such a great vertical tilt, but the system is not yet vertically stacked either. Thermal advection or temperature change pattern has reached its peak development, and the surface low is removed from the warm air mass. So now we're starting to cut off the temperature contrast. The air masses are mixing together, and the system eventually is going to weaken. As we get into the dissipation stage of a baroclinic low, the system will evolve into what's known as a cold equivalent barotropic low. Barotropic meaning there's no more temperature advection, there's no more temperature change. And usually what we have is just a pocket of cold air aloft with an upper level low as the remnants. So that 500 millibar low, 18,000 feet, develops more closed contours, height contours. It becomes more circular, less wave-shaped. Vorticity center is still strong, but is centered in 500 millibar low, where the vorticity and height contours are essentially parallel. You get weak positive vorticity advection, weak PVA. That indicates a lack of upper level divergence. So now, at the lower bottom portion of the surface low, we're having basically a filling effect to where the barometric pressure is rising as the surface low and the upper level low become more vertical to each other. Here's an example. These two systems are pretty much vertical to each other. The surface low is at the bottom portion of the diagram. The upper level low up at 18,000 feet is basically directly straight vertically above the surface low. So again, you notice in the top portion of this diagram how the black solid lines of height contours are parallel to those dashed lines, which are your thickness lines. I'm sorry, the isotherms, lines of equal temperature. So we're not exactly getting any more type of advection going on at this point. So the surface low in the dissipation stage is beneath the upper level low. System's now more vertically stacked. The surface low will fill. Basically that means the surface pressure is rising, the storm is weakening, and it will disappear long before the upper low disappears. So when we talk about the atmosphere, the surface low pressure system is going to fill and dissipate, and the only thing you're going to have as a remembrance of that storm is an upper level low if you're looking at upper level charts. The surface low is well back in the cold air mass and virtually removed from the thermal gradient, so that surface low is now shifted back northwest towards the colder air mass. So we no longer have that thermal or temperature advection pattern as it's weakening, and the isobars and thickness contours become parallel, or the thickness gradient becomes well removed from cyclone location. And once the occlusion has begun to separate itself from the surface low, then we definitely know that we're in the dissipation stage. So that wraps things up on the baroclinic lows. They go through a definitive life cycle. Kind of did some reviewing here, but also we went through the life cycle of a baroclinic low, starting with wave intensification. Then we get to a mature wave stage. This is when the surface low reaches max intensity. Then we went to the dissipation stage, where the upper level low and the surface low are pretty much stacked straight vertically, the upper low vertically above the surface low. So now we're going to talk about our friend of fair weather. We have those nice, beautiful, clear blue skies, those wonderful fall days where it's just blue skies, plenty of sun. That's usually associated with high pressure when the air is sinking in the atmosphere vertically. As air sinks, it dries and it warms and it's very stable. So we're going to talk about the development of these baroclinic highs as they transit from the source region, typically in Canada, on down into the lower 48. First, let's start talking about formation. When I say anticyclogenesis, it's a fancy term to say the development of an area of high pressure or the strengthening or building of that high pressure. Okay, so anticyclogenesis is favored by certain large-scale conditions, just like we talked about with baroclinic lows. With the long wave pattern, the jet stream at 30,000 feet, you typically have the development of a high pressure system or the building and strengthening of that high at and just downstream from the long wave ridge axis. And I'm going to show you what this looks like in a minute. That jet stream pattern, the jet stream is not only important as far as the steering pattern for storm systems and these baroclinic highs, but it's also important as far as where is the air sinking in relation to what's known as jet maxes or jet streaks. Anticyclogenesis typically occurs under what's known as confluent flow aloft. That's when the height contours get closer together. They're getting closer together and kind of running into each other, and that's resulting in a addition of mass aloft. And as that mass is added aloft in the upper atmosphere, it's got to go somewhere. As these airflow, these air streams meet, the air must sink. We have a lot more mass aloft, and that is going to result in convergence aloft. So for this reason, anticyclogenesis is common just downstream from the confluent upper level flow, typically downstream or to the east of the ridge axis. The gradient wind relationship also promotes speed convergence between supergeostrophic winds in the upstream ridge and subgeostrophic winds in the downstream trough. And there's differences in speed and movement of air parcels as they move through the jet stream, and we're not going to get too technical about that in the video. Here's a favorable area for high pressure systems to develop, the baroclinic highs, typically going to occur east in the northern hemisphere, east of that ridge axis. Notice the sawtooth black saw line and where the lines are blowing up to the greatest heights. That is the ridge axis, and the blue or shading indicates where high pressure typically forms when we're talking about the jet stream pattern, the long wave pattern. But to the east of that long wave ridge axis is the best spot for formation. Here's an example of confluent flow. Now the solid black lines are indicating height contours, and you notice how when they come together or get closer together, they kind of run into each other. This is where the convergence is occurring, confluence or convergence aloft, the addition of mass aloft, and that's going to result in a sinking air motion. As air sinks again, it dries and warms, it produces fair weather. Now, just like we did with baroclinic lows have support at 18,000 feet in the atmosphere at the 500 millibar level by those shortwave troughs. Similarly, baroclinic highs at the surface have upper level support in the form of what's known as upper level shortwave ridges. And so your surface baroclinic high is going to stack back towards the upper level shortwave ridge. So self-development depends on the presence of upper level ridge. In general, vigorous anticyclogenesis will not occur without that major shortwave ridge to support the surface high. So again, it comes down to having the upper level support for these surface highs to really get strong. The low level structure, anything baroclinic involves temperature change. So baroclinic highs are going to derive their energy from baroclinic instability of the north-south temperature gradient. So similarly to the baroclinic lows, the low pressure systems, high pressure systems are also going to derive their energy from the baroclinic instability. They're going to feed off that large temperature difference, across the latitudes from the high latitudes to the low latitudes. The strongest temperature gradient is going to occur along the polar front. With strong baroclinic highs, they're typically associated with convergence aloft. And now, instead of PVA, we're looking for negative vorticity advection to interact with this baroclinic high at the surface, and that is going to result in sinking air motion, convergence aloft, sinking air motion, and low-level divergence, air spreading out at the surface. So surface divergence destroys fronts because fronts require lifting, vertical lifting, whereas surface divergence promotes spreading out, sinking air motion at the surface. Thus, you will never really see a baroclinic high associated with the front. Now, baroclinic highs, where do they move? They tend to follow the passage of a cold front. So in the wintertime, we get this nice, strong cold front to blow through, and if you're living in a particular location, all of a sudden it's like, wow, it got cold. It kind of cleared out. The sky cleared out. You're most likely under the influence of a baroclinic high pressure system, as they typically follow the passage of the cold front. As a high tracks towards the strongest colder air advection, CAA, the pressure rises drastically, and that creates a path of least resistance for that baroclinic high as it moves. Baroclinic highs typically move towards the southeast in the northern hemisphere across the U.S. due to this fact that the strongest cold air advection is typically right behind the cold front to the southeast of that high. Now, the self-development process of a baroclinic high, just like we did with the baroclinic low, the baroclinic high has stages of development. The first stage is known as intensification, and we see that self-development process. The self-development process referring to if we get one thing to happen, all the other dominoes fall in place, and it kind of just works its way down the line. So the first thing we have, when we talk about the self-development of baroclinic highs, the baroclinic highs are going to tilt with height and stack from the upper level shortwave ridge. You're going to stack basically up towards the mid-levels of the atmosphere, the surface baroclinic highs. And you're going to have upper level convergence over the surface high, which is causing the high pressure to build or get stronger, because if you have upper level convergence, the air sinks, and as air sinks, it adds more weight or more force per unit area to the surface, and that's going to cause the barometric pressure to rise. Anticyclonic circulation, that's that clockwise flow of wind, strengthens once that happens, and that anticyclonic circulation will strengthen the temperature advection around the high. This pattern causes a shortwave ridge to build and the shortwave trough to deepen. Anytime we have a stronger temperature gradient, that kicks in further deepening of the shortwave trough and the building of the shortwave ridge aloft. So since the ridge becomes more anticyclonic, there's greater anticyclonic turning, sharper anticyclonic turning, or clockwise turning around the high, the vorticity minimum in the ridge becomes even smaller. So that value of vorticity is going to get smaller and smaller. Since the trough becomes more cyclonically curved, the vorticity maximum becomes even larger. So convergence occurs ahead of the shortwave ridge, and the upper level convergence is going to strengthen. You're going to get negative vorticity advection, or NVA, located between the ridge and that downstream trough, and that's going to increase, indicating stronger upper level convergence. The increased upper level convergence then causes anticyclogenesis to occur, and the pattern continues as a positive feedback loop. Again, one thing happens that sets into motion the other things, and that's known as a positive feedback mechanism, where one particular mechanism feeds off another. The limit on strength of the anticyclonic gradient wind impedes development of the high. So there's a certain limit to the maximum strength of the gradient associated with high pressure development. Putting both the self-development of the highs and lows together in one graphic, great graphic, for the baroclinic low on the left with the frontal boundaries, the cold and warm front, you have a stacking back of the troughs, 850 millibars, 700, and 500 millibars. There's an area of positive vorticity advection, again, ahead of the major shortwaves trough, in that case, and that's going to cause self-development and kick off the development of the baroclinic low, that low pressure storm system. With high pressure baroclinic highs, you get cold air advection on its front side, and it also stacks back aloft to up to 500 millibars with that major shortwave ridge. An area of negative vorticity advection is going to enhance the upper level convergence, which is then going to result in sinking air motion and anticyclogenesis, the building and strengthening of the high. So this is really good stuff. Here's a couple more boxes to kind of show you just generally the motions, and that's a great slide again. Just, the connections between lows and highs is a constant interplay in the atmosphere, the circulations between both of these pressure systems. All right, so and also remember the development of baroclinic highs. What baroclinic highs really want is local decreases or drop-offs in the thickness values near the center of the anticyclone. That's going to be more beneficial when we lower the thickness values, meaning we have colder air towards the center when we're talking about baroclinic highs. And if that temperature decreases in a layer, the layer thickness will also decrease. Temperature and thickness are directly proportional to each other, so if I lower my thickness values, the temperature also lowers. So colder temperatures moving in, cold advection lowers the virtual temperature. If the air is dry, that's also favorable for the high to get stronger, to build. That's also going to be favorable. You get local diabatic cooling and drying of the air as the high pressure center moves out from its source region in Canada into the lower 48 into the US. That's going to, if you get local diabatic cooling, let's say the high moves over a cooler, drier surface, you may get removal of sensible and latent heat from the air. And this could lower the virtual temperature even further. Now, just like I talked about with baroclinic highs and with storms, or baroclinic lows in storm systems, each cyclone's got braking mechanisms. We talked about that. We talked about adiabatic processes, and we talked about boundary layer convergence as the winds and the pressure gradient get stronger. Friction acts to fill the bottom of the air column. There's also braking mechanisms with the development of baroclinic highs. These mechanisms, again, a braking mechanism is a mechanism which slows down and eventually stops the further development of the baroclinic high in this case. And with the development of a high, other processes called braking mechanisms begin. They eventually completely offset the self-development process and prevents the system from building indefinitely. If we did not have braking mechanisms in the atmosphere, cyclones would grow as intense as they wanted to, and there would be no breaking point or no limit to their strength. The same thing with baroclinic highs. These high pressure systems will continually to build and get stronger and stronger and stronger and stronger without any braking mechanisms. But thankfully, the atmosphere puts these braking mechanisms in place to help alleviate the intensity of these systems. Now, braking mechanisms for highs are much more efficient than for low pressure systems. Here are the types of braking mechanisms for the baroclinic highs. Boundary layer processes play a role, again, in acting as braking mechanisms. Once you have your anticyclonic or clockwise circulation increasing around the high, the low-level divergence increases due to increased frictional influence of the faster wind speed over ground. And also you get these pressure rises in the high pressure center, which produce an isobaric wind, which enhances surface divergence. So bottom line here is if you have low-level divergence that's stronger, then that's going to result in an increase in friction. As the low-level divergence spreads out along the Earth's surface, that wind is going to interact with many influences. Think about wind as it blows across the ground. You have trees, you have houses. That's going to result in a lot of frictional impacts, and that is not going to be favorable. Here is the boundary layer divergence situation. Friction is going to cause the cross isobar flow outward away from the center of the high pressure. That's the way this circulation and the wind blows outward away from the highs. Adiabatic processes. The vertical motion field intensifies when you have adiabatic process. Colder air advection, and then the upper level converges aloft force what's known as subsidence. Now, cold air is heavy and dense, it wants to sink. And then you get upper level convergence, and that's going to result in the accumulation of mass, and that's going to result in a sinking air motion. The problem is as air sinks, it warms. So if the air sinks and warms too much, that is going to basically offset it's going to stop. It's going to act as a braking mechanism. It's going to stop the building or strengthening of the high. Remember, the center of high pressure systems, the baroclinic highs, want cooler air, but as air sinks in the center of these highs, it's going to undergo subsidence and warming. So that subsiding warm air will dry adiabatically, the air dries out. This compressional warming offsets the cooling. And so we want lower thicknesses in the center of high pressure systems. We're not going to get that when the air is sinking at the center of the high. So this helps limit strength of the baroclinic high. Now, changes in the structure of the baroclinic highs during development, air masses. A baroclinic high is typically going to form back in the colder air, the cold air side, or to the northwest, to the north of the polar front. Early in their life cycle, the high is associated with a polar air mass, often in a polar source region where cold ground enhances the local decrease in thickness and promotes anticyclogenesis. So typically, baroclinic highs form over flatter terrain. That's a great source region where the winds are fairly light over a fairly cold ground. And that's going to occur typically up in Canada for our baroclinic highs that come down in the wintertime. As the high moves, as the high matures and goes through its self-development stages, as it moves further southeast, it's going to eventually be moving over a warmer air mass, a warmer ground. And as that high moves over the warmer ground, it's going to result ultimately in being absorbed into the subtropical ridge. As a high moves out of its cold, often snow-covered source region, it moves over warmer ground, or even worse is if you have a continental polar high, a high pressure in the wintertime that comes down from Canada and moves out over the relatively warmer waters of the Western Atlantic. Any warmer ground or water is going to result in increases in the temperature and moisture, which is going to raise the thickness values, and that is going to promote the dying off of the high pressure system or the weakening of the high, anticyclogenesis. Now, where do baroclinic highs typically reside or live? They're normally on the plus N side of the polar front jet. When I say plus N, to the north of the polar front jet axis in the colder air. On occasion, a high may move in other directions in response to changes in the long wave pattern, that jet stream pattern of troughs and ridges. That high can move in other directions too. So the high will move basically southward of the polar front jet while undergoing the self-development process, and it eventually become a warm core high, being absorbed ultimately, in a lot of cases for the U.S., it's absorbed into the subtropical ridge in the Atlantic over the Atlantic Ocean. And basically, as far as weakening mechanisms, baroclinic highs weaken in one of two ways. First case is where they lose their upper level support, where your upper level convergence or the addition of mass aloft will diminish, or worse yet, if you get upper level divergence replacing the convergence aloft, that is going to remove mass from the upper levels of the atmosphere. That's actually going to promote rising air motion in high pressure systems like sinking air. So without the upper level support, the high will eventually weaken. And then the high can also go through its entire life cycle as it moves out of its source region from Canada and eventually be absorbed into the warmer core subtropical ridge. Again, as the high moves southward, the center of the high will warm via a couple things here. First is a sinking air motion within the center of the high. As the air sinks vertically, it's going to warm, and then also contact with warmer ground or over warmer water. So the southward movement of the anticyclone or the high pressure system will force the vertical depth of that cold divergent air to become shallower and thus more quickly modified. The more shallow the colder air dome, the quicker it can be modified. So as that temperature contrast decreases, the high will eventually weaken because we're talking about a baroclinic high, and it's going to tap into major temperature or thermal gradients. Once we lose that temperature contrast or gradient, the high will weaken. The high will eventually be absorbed again by the subtropical ridge and become a warm core high. Okay, so basically this is the track of a baroclinic high. It's going to form poleward or to the north. The dark solid line on this image indicates the center of the jet stream, basically the jet stream axis. The dashed lines outline the outer edges of the jet stream. And so you notice where the high pressure initially forms to the north of the main jet stream axis. So see how it's above the solid black line. And then the arrows show its eventual progression movement moving towards the areas of strongest cold air advection in the lower atmosphere. And eventually it's going to modify, it's going to warm as the high moves over the warmer ground. As it moves south, it's going to weaken the high pressure system. So summary of the process, the life cycle of a classic baroclinic high. Pedersen in 1956 described these steps. The first step is you get a classic baroclinic high to develop, and it will form as a bubble of high pressure from either the subtropical or Canadian high. The high will intensify beneath the upper level convergent quadrant ahead of a shortwave ridge, and it will normally move in an east or southeastward direction towards the strongest cold air advection. Eventually, air at the center of the high pressure will eventually warm, again due to sinking air motion subsidence and heating from below. The ground is warming. For example, as the high gets all the way down towards the southeastern U.S., the air or the ground is warmed drastically compared to where it started in Canada, where you had snow-covered ground. The high is eventually absorbed again in the subtropical ridge. All right, that wraps things up. I hope you enjoyed this presentation. Again, on mid-latitude systems, this actually is the third and final part of the training. Again, dynamics in the atmosphere come into play so significantly in the development of these baroclinic lows, these storm systems, and the baroclinic highs that typically follow the cold fronts. They come in behind the cold fronts, especially in the wintertime. You get very strong low pressure systems, and eventually those atmospheric low pressure waves dissipate with higher pressure building in behind, so your stormier weather eventually becomes nice and clear again as the baroclinic highs move in. All right, that wraps things up. Spot on weather. I really hope you enjoyed this presentation. I am very pleased. Thank you so much for subscribing to this channel. I'll be back with an update on the weather soon. Take care, everybody. Have a great, great Wednesday. Take care.